This video introduces VT-Refine, learning bimanual assembly with visuo-tactile feedback via simulation fine-tuning, a collaboration between Columbia University, NVIDIA, and UC San Diego. Humans rely heavily on touch for precise assembly. However, even with touch, if you don't have an enormous amount of data, imitation learning still suffers for tasks that require high precision. We were definitely not satisfied with this performance. To improve, we built a digital twin with high-fidelity, GPU-parallelized tactile simulation. Here you can see the tactile signals, real on the left and simulated on the right, showing a very close match. Given the simulation, we first pre-trained the policy using a small amount of real-world demonstration data. We then fine-tuned the policy in simulation with reinforcement learning, which enhances both exploration and robustness. Finally, we transferred the refined policy back to the real world. The robot can now perform precise bimanual insertions, even recovering from initial misalignments by adjusting through touch. Before diving into simulation, it helps to first understand the tactile hardware. Our sensor, FlexiTac, employs a resistive sensing matrix to efficiently convert mechanical pressure into electrical signals. A key improvement over our previous sensor in 3D ViTac is the use of two flexible printed circuits, FPCs, arranged as orthogonal electrodes, replacing the manually aligned conductive threads. This modification not only increases the spatial resolution to 2 millimeters, but also enhances signal consistency. The improved consistency is crucial for achieving robust sim-to-real transfer. Now let's take a closer look at how we build tactile simulation. We begin by creating a mesh over the top surface of the robot gripper. On this mesh, we sample tactile points at the same density and resolution as those in the real sensor. For each tactile point, the interaction with a rigid object is modeled using a Kelvin-Voigt model consisting of a linear spring and a viscous damper connected in parallel. Each sampled tactile point independently computes its contact normal force by interacting with the object's signed distance field. After we get this high-fidelity tactile simulation, let's see how we utilize it for our two-stage policy training. We begin by collecting a small real-world demonstration dataset to pre-train a diffusion policy. During each demonstration, we record visual and tactile inputs, robot joint states, and action commands. As we have a digital twin in simulation, as well as tactile simulation, we directly transfer our pre-trained policy into simulation and fine-tune it in an end-to-end manner using diffusion policy optimization. The benefit is obvious: a small amount of data collected within half an hour and a sparse reward that minimizes reward engineering. We use two different bimanual robot setups, both equipped with an egocentric camera and 4 FlexiTac sensors covering a soft gripper. We evaluate our pipeline on 5 different assets from Automate. As shown in the video, the robot can successfully complete the tasks with robustness, even recovering from an initial inaccurate attempt. Importantly, all 5 tasks are trained with all amount of real data and sparse rewards in simulation, making our approach easy and fast to adapt to new tasks. To demonstrate the robustness of our policy, let's look at some comparisons. With our method, even when in-hand sliding occurs during grasping, causing the initial insertion to be inaccurate, the two hands coordinate to perform an in-hand adjustment and complete the task. In contrast, even with touch, policy without simulation fine-tuning continues to apply force when the insertion is misaligned, leading to failure. Here are more examples of how the pre-trained policy may fail to recover from unexpected local contact dynamics. Touch feedback also plays an essential role in achieving success. With tactile feedback, the robot can insert more accurately and combine this with fine-tuned wiggling behaviors to succeed. In comparison, a vision-only policy may perform the same wiggling behaviors but in the wrong location due to visual occlusions. Here are more demonstrations showing how vision-only policies fail to exploit these fine-tuning behaviors effectively. In summary, VT-Refine shows how leveraging a small amount of real-world visuo-tactile data combined with sparse reward fine-tuning in simulation enables precise and robust bimanual assembly. The tactile simulation and real-to-sim-to-real techniques provide useful tools and insights for the community to pursue further research. We believe this framework brings robots one step closer to mastering human level dexterity in contact rich tasks.